Alexander, who is in Germany. So let's start our today's seminar with Alexander Chudnovskiy, who would be talking about Sachdev-Ye-Kitaev superconductivity, quantum Kuramoto, and generalized Richardson models. So Alexander is a frequent visitor at PCS, so some of you have already seen him last year and perhaps even the year before. So he received his PhD from the University of Würzburg and then was postdoc at the Ohio University in the US and Halle University in Germany. And since 2001, he's in Hamburg, first as a lecturer and now since 2006 senior lecturer, and his research interests basically center around theoretical condensed matter with combination of out of equilibrium, disorder, and interactions, which I guess many of you inferred from the title. So let's welcome our speaker.
Thank you. Thank you very much. Thank you for this nice opportunity to give this talk and for the invitation to give this talk. And I hope that in the future we will have the possibility to give a talk at present, seeing each other not only on the screen. So this work is basically the continuation of my investigations, which are already probably 2 or 3 years long, about the Sachdev-Ye-Kitaev model, which appeared some time ago as a model which connects solid state physics basically with gravity theory. But what I will be talking about concerns only the solid state side of this model. And from the point of view of the solid state physics, this model is interesting because it was able to reproduce some properties of strongly correlated systems, in particular the systems that become high TC superconductors at low temperature. And that is why the search of possibility of superconductivity in the Sachdev-Ye-Kitaev model was for the last year or the last 1 or 2 years, it was very intensive attempts to find superconductivity either in the initial versions of Sachdev-Ye-Kitaev model, which I will be talking about in short, or by modifying this model. And in that way, with a big, so to say, a big goal to describe with the help of Sachdev-Ye-Kitaev model the properties of high TC superconductors. This goal is not reached for now, but nevertheless there is some progress, and this work represents some step, probably some step toward this large goal. The work I will be presenting now is done in collaboration with Hanteng Wang and Alex Kamenev from University of Minnesota in USA, and with Alexander Gorsky from Institute for Information Transmission Problems in Russia. And there is a reference here. This work, the results were published in Physical Review Research this year. So let me go. So first question is, I already partially addressed this question. So why do we need, why superconductivity in the SYK model? And the answer is the following. So first of all, in its initial version, as it was formulated, I do not show Hamiltonian here, but nevertheless, in its initial version of the SYK model does not have a superconductivity, a superconducting phase. What is SYK model? Basically, you have a number of sites, and you have fermions interacting at each 4 sites. So your basic Hamiltonian can create, can annihilate operators on 2 electrons on 2 different sides of the model, and then create those electrons on 2 still other different sides of the model. And all this creation and annihilation processes of pairwise creation of and annihilation of electrons happens randomly. I will go to details of this Hamiltonian in the next slide, but still, the results for now are the following. So if one investigates the SYK model, one can reproduce some interesting features which are not superconductivity, but those are features which are detected experimentally in high TC superconductors at higher temperatures, at the temperatures above the superconducting transition temperatures. In particular, SYK model can reproduce the behavior of the so-called strange metal, which means that one can get resistance of the substance proportional to the temperature in a very large range of temperatures without seeing any threshold or cutoff at high temperatures. More or less, moreover, and it was the interesting point that if one looks at this SYK, as I said, SYK can one single SYK model, one can consider it as a kind of a grain with many sides on the grain and electrons interacting at all sides with, so to say, infinite range interactions. So every side interacts with which is each other side. So now if one considers single SYK as a grain, and then consider a system consisting of many grains, many such SYK grains coupled, for example, by the tunneling, then one can get the phase diagram, which is shown on this picture, and this is a reference of Balance and co-authors. And in this phase diagram, one can see that depending on the tunneling is V here, V and temperature is T, and J is the normalization of energy, typical SYK energy. Anyways, one can see the transition between the Fermi liquid behavior of this system and the behavior which is characterized, which is called strange metal, which means the incoherent transport with the resistivity proportional to the temperature. This was interesting observation. And the same strange metal is known to be observed in high TC superconductors. Moreover, if one analyzes this model in more detailed analysis, shows that basically there is another interesting feature of this model, namely that there is an insulating phase. If one lowers the tunneling lower than some threshold, one can find an insulating phase at the very small tunneling. So one has basically three phases: insulator, Fermi liquid, and strange metal phase. And so to say, topologically considering, it is looks similar to the phase of high TC, to the phase diagram of high TC superconductor, at least superficially similar, where there is a Fermi liquid, there is a insulating phase with magnetic properties. Magnetic properties are not here, but anyways, there is an insulating phase, Fermi liquid phase, strange metal phase, and of course, superconducting dome at low temperature. The superconducting dome is not here. But all these two, basically these two, and there is a series of other works which are also showing such strange metal behavior and insulating behavior. All these inspired investigations and search for superconducting phase. And there were several attempts during basically last 2 years to detect superconducting phase in the SYK model. So now let me make a step back and introduce the initial SYK Hamiltonian, which is written here in the first line. One has sites numbered by index I, J, K, L, I, running from 1 to N. N is assumed to be large and basically tending to infinity. And then the basic elementary process described by the Hamiltonian is annihilation of 2 electrons or 2 fermions on the sides L and K, and creation of 2 another electrons at this fermions at the sides I and J. And this constant amplitude which describes this interaction, it is a random number, Gaussian distributed, and in the initial model, it is complex valued. The only non-linear, non-zero, non-zero average is the variance of JIJKL. So this is a Gaussian distribution with zero mean and with the variance given by this condition. Now, this model as such is formulated for spinless fermions and with complex valued J. And this model does not show any superconducting phase, and there is basically no hope to obtain this superconducting phase, superconducting ground state, because first of all, not only because electrons are spinless, but because J's are random and complex valued, which means basically that each JIJKL introduces kind of a random flux into the model. And such random fluxes would destroy any possible superconducting order. So since then, one tried to modify the SYK model somehow, probably introduce minimal possible modifications that would favor superconducting state and maybe induce superconductivity. So first idea was to remove, so make J real, so remove those random fluxes in the model and include spin in such a way.
Alexander,
Yes.
I have a question already. So how do the properties of even of the original SYK, even before you start modifying it to get superconductivity, how does it depend in general on the properties of the of the interaction JIJKL? That is, I could take it random, but I could vary the distribution, or I could take different distributions, or I could, for instance, go from random to, I could interpolate from random to non-random one. So what would change?
Yeah, so basically it is like as long as you keep average J 0 as here, basically nothing will change. As long as J remains random and with zero average, which is very important, with zero average.
But the type of random, sorry, the type of randomness doesn't matter.
Well, so no, in more details, I would say this. I don't know what happens if J is not non-Gaussian distributed.
Question from me. Why is it important that the average is zero? You said it's very important. Why?
Because if average is non-zero and J is, and you make J randomly distributed, but for example, randomness is very weak and you have non-zero average, then you have a system with constant, basically two particle interactions. And as far as I understand, the properties will be, at least the properties will be very different. This is the least what I can say in the following. So what happens then? I basically don't know whether anybody consider this, but let's say this, as in this original model, the basic property is the following: that this randomness J squared is the only energy scale of the Hamiltonian, and each correlation functions. Well, what one can then basically investigate is the behavior of the correlation function as a function of time or at finite temperature. And the behavior is the following: that the correlation function is, for example, any correlation functions, and basically starting from the one particle, for example, Green's functions of electrons or density correlations functions, all of them will decay as a power law with the time, in imaginary time or in real time if the temperature is zero. If the temperature is non-zero, then they will be decay exponentially in time. Then this power law will be modified to exponent, and the exponent basically will be determined by the temperature measured in the units of J. So any energy is measured in the units of J. This is but the most important and interesting property is this power law of decay of correlation functions. and this power is independent of J. For example, in this model, like it is formulated here, the Green's function, simple particle Green's functions decay as 1 over square root of time, imaginary time or real time at zero temperature, and then and this power is fixed. The only effect of J is rescaling over the overall time or energy scale, nothing else. So if now you introduce some non-random J, then I cannot give you precise answer, but I think that there will be no power law decay anymore, and the properties will be quite different. And I don't know the answer. I don't even know whether anybody considered such system. There was no such interest.
Well, in a very limiting case, you could come back to the Hubbard model without any single particle Hamiltonian part to it. So, but anyway,
if you make it local,
it's very important that it is zero. So,
yeah.
In terms of superconducting attempts to create superconducting phases.
In attempts to let me see this in the next slides. You will see that I will in my attempt to create superconducting phase, I will introduce Hubbard interaction in some way, but this will be non-random. But let us postpone. You will see it in a few minutes what will happen. Okay. So, anyways, as to give such a small, so to say, account of what has been done, I can say the following. So, first of all, so J remains random, and if J remains random, one tried to remain this randomness because of first of all power law decay, and from this power law decay indirectly, it follows that there is a strange metal. So I think that if you make J non-random, what you will physically lose in your phase diagram is this strange metal, which was one of the, so to say, initial points, which was the inspiration to search or to apply it in some way to high-TC superconductors. If you lose this feature, then probably that's why it was nobody looked at it very attentively. So whether making a J real and including spin, both these attempts did not succeed to create superconductivity. But
Alexander, yeah, sorry, I mean, exactly at this point, I have a question again. Making J real and including a spin didn't lead to superconductivity, keeping the Gaussian distribution.
Yeah, keeping the Gaussian distribution, exactly. Again,
yeah, but do you think like taking discrete one would change anything? So if you just take J that has plus J and minus J value.
Well, I don't know exact answer. I can only, what I know is the following, that if you like consider your distribution in terms of cumulant expansion, so you say that your J's have not only the second cumulant, but also the fourth power and higher powers non-zero. Then what I know is in terms of cumulant, as long as you keep only a finite number of them. What I know is that what happens is that power law, the dependence of correlation functions will remain power law. I'm telling about the correlation functions as functions of time difference. So it will remain power law, but the power will change. That's what I can say. And it does not look that you get some new phase out of it. I don't know what happens if you make the distribution like bimodal, so to say, plus J and minus J. It's much too extreme that I don't know. I don't know. I don't know, and I know that I did not see that anybody tried this thing.
Okay,
may I ask a question? You have these sites I, J, K, L. Is it real sites in space? I mean, positions on space, or it's just abstract?
You can think about it. It's rather abstract in that sense that they are this lattice, so to say, is fully connected. At each side there is no distance in that sense.
So my question is, I mean, if you're talking about superconductivity, we should imagine some current going in some space and so on. So you should have at least some hopping between sides. Now you have this hopping, peculiar hopping of pairs of electrons, so to speak. Where is this single electron hopping?
No, it's not there. No
But okay, if you don't have it, could you have flow of electrons as a current and so on in space if you not connect the sites with a single electron transfer?
If you don't introduce single electron transport, the only transport of charge you can have is the transport of pair, is through the pairs. No single electron charge transport. You can still have charge transports in the sense of charged pairs of electrons.
And what it is behind how you quit the single electron tunneling in reality? What you have in mind? I mean, that considering
in reality, there are following possibilities. So first of all, you can consider 2 or more grains, as many people consider. So let's think about this Hamiltonian, which is written here as a single grain. Now you take 2 species of it, 2 grains, A and B, let's say, and you can introduce, for example, however small or not small, depending, but better small, tunneling between those 2 grains.
So you mentioned this. So you consider this as a peculiar metal, but transport is intermetal tunneling.
If you wish, yeah. So one of the possibilities to consider a continuous medium out of this is to think about it as a number of grains, and those or network of grains.
And if you're talking about superconductivity, in this case, you have to consider superconductivity as a property of single grain or this tunneling.
As a property of single grain.
And what would be the feature of this property? I mean, what's make it, we say superconducting means that it's conducting in super way. I mean, if it is grain with such a, what kind of property would manifest this superconductivity of this single grain?
So you can, yeah, I understand. So one can answer, so to say, in a theoretical way, it is the appearance of superconducting condensate of electron pairs, superconducting order parameter of diagonal long-range order. I will be talking about this during my talk. This will be probably the main point of my talk. Yeah, now you can ask this question in the more experimental posed ways, like how can you imagine an experiment which will show some features which will, so to say, demonstrate or prove that this is the superconductor. So you can arrange, you can imagine, and you can imagine, so to say, 2 or 3 grains arranged by tunneling, and you can introduce magnetic flux in the sense of a difference of the phase on weak links.
Yeah, I understand. I understand.
And then you can see the reaction of this system on this.
In short, you can say that this superconductivity is built inside of this molecule or dot manifests itself in coherent tunneling, which occur in this granular thing. Tunneling become coherent. I mean, it's
Josephson effect.
Josephson effect. Yeah. Thank you.
Well, so, and as I say, so the last to mention the last attempt successful attempt to introduce superconductivity is to couple this system with to auxiliary phonons. This is a work of Esterlis and Shmalian, and it basically in both these works. So or you can introduce specific symmetry, which makes JKL rather artificial, I would say, but nevertheless. And then you can see the superconducting instability in the sense that you have instability in the Cooper channel, of the mode of the Cooper channel. Not that I'm sure that it is a superconducting order parameter, but nevertheless, one can obtain instability. In both cases, so to say, the bottom line is In order to include superconductivity, you need to distort the model. You need to modify the model in some or the other way. The pure model does not show superconductivity as such. Till now, all attempts till now were not successful. And the subject of my talk will be also about simplest modification, which lies basically at hand. And this is the simplest possible, probably, modification of this model, which should show the superconductivity. And this, I will call this modification SYK+U, which means basically that you need attraction between electrons. So what you do, you write down the SYK model, but for spinful electrons. This is the SYK Hamiltonian, and sigma prime are spins up or down with real J couplings. And because it is known that this is not enough, additionally, you introduce Hubbard interaction as Hubbard attraction, exactly. Not repulsive, but attractive Hubbard interaction. So U here is positive, and sign minus is specifically to show that this is an attractive Hubbard interaction, which will favor creation of on-site electronic pairs. So you localized electron pairs. If Hubbard interaction is very large, then the model will tend to have localized electron pairs, and J, the SYK term, will describe the hopping of pairs from any two sides to any other two sides. So now, how can one imagine the superconductivity, or what we envision, so to say, as the establishing of off-diagonal long-range order in this situation? So the elementary process described by the SYK Hamiltonian, as I told already, is the following. One have two sides, K and L, with electrons, say, up and down, with spins up and down, electrons with spins up and down, and the single action of the JIJKL will transfer those two fermions or two electrons from the sides KL to other sides I and J. The simplest understanding of the superconductivity or of diagonal long-range order can be gained if one goes to the limiting case of very large U. In the limiting case of very large U, meaning U is much larger than this J, which is the variance of the distribution of those Gaussian couplings, then the situation is rather simple to imagine. One has pre-localized pairs. So at each side, basically, there is a pair of electrons, or Cooper pair, one can call it. And then this SYK part of the Hamiltonian will facilitate the motion of those Cooper pairs along the lattice. And the elementary act of hopping of a Cooper pair should include two actions of this SYK hopping JIJKL in the following sense. So single hopping will take one spin from I and one spin from J and transfer them to the intermediate state, where one has occupied four sides singly occupied, I, J, K, and L. This intermediate state, if U is large, will be an excited state with a large energy of the order of U. And then the subsequent hopping event will transfer the full pair IJ, two spins from the side I completely to the side J. So basically what one gets out of this is that the typical scale of coupling between those superconducting pairs, so to say, so Cooper pairs, is of the order of J squared divided by U. But this is in the limit of the very large U, where one can expect that in such way, the superconducting coherence will be established between the pairs and different sides, pairs of electrons at distant sides and over the whole grain. The question is, however, what happens at small U? And not only at large U, but at any values of U. And Myself and my collaborators, we performed an investigation of this model, both numerical and analytical investigation. And our investigation ended in this phase diagram, which I will describe, which will be the subject of the rest of my talk, basically, where, to summarize, we have the following. So in the horizontal axis, there is a coupling U, Hubbard U. It is negative. And this is an absolute value of U. And on the vertical axis, this is T, and all energies are measured in the units of the SYK, typical SYK energy J. And one can see that one has, first of all, at T equals 0, one can observe a quantum phase transition between a normal phase and a superconducting phase when U is increased. So which means that if U is very small, finite but very small, then still the phase is not superconducting. And small U is not enough to induce superconductivity even at 0 temperature. But then there is some critical value of U at which superconduction correlation of diagonal long-range order sets on, and the system becomes superconducting. And if you increase temperature, then you see this phase boundary, which looks like this. It is first goes up, and then if U is larger, then it goes down. It's one can maybe imagine this kind of like a superconducting dome, but this going down continuous. It goes down continuously without showing any, so to say, it goes basically as 1 over U here. This line without ending, without stopping, and what happens then we cannot answer because we have only single grain. Basically, to get kind of a Fermi liquid out of it, one should consider basically an array of those. Maybe then we can answer what happens at very large U here. Maybe superconductivity stops. But till now, this is the phase diagram. But already this phase diagram has some peculiarities in the sense of what happens, what is the physical character of this system, and what happens around the quantum critical point here, where the transition between superconducting and normal phase takes place.
May I ask a question? Could you calculate heat capacitance or something, I mean, around this transition, how it would behave?
I did not, but I can.
Is it similar to BCS or?
I think yes. So I expect that it will be similar.
So there must be some quasi-particles in this system similar to quasi-particles in superconductors.
Yes, and I will, yes, there are, and I will stop on it. I will mention it.
Okay.
In my talk.
May I ask a quick question? What about the normal state? Is it just Drude model, something like that?
Oh, no, it's rather peculiar. But I will tell you about it. There will be details about those normal states. Just at high temperatures, it's SYK. I can shortly say the following: in high temperatures, it is SYK. What one sees at the SYK without any U. At low temperatures, there is an insulator, some kind of insulator, and how it happens. It's not. I cannot tell you in details, but basically, I think it is a crossover from thermally. It is a thermally activated behavior, which at high temperatures looks like usual SYK. But let me go in. I will explain it in more detail.
Yeah, but usual SYK means metal. It means finite conductivity.
Absolutely, yes. And this will be finite conductivity at high temperatures. At low temperatures, one can see that there is a tiny gap. So it is thermal activation. But
Okay.
this gap, the thermal activation energy, is very low.
Thanks.
So now I will stop about by talking about the phase transition. I will stop on 2 models. I will develop 2 models and explain. The model for a quantum phase transition, I will show that this is basically described by a kind of a model which is known as a model of synchronization of oscillators, which is called the Kuramoto model. Was introduced by Kuramoto. about 20 years, it's in 70s still, but as a classical, and this here it is will be a quantum version of it. And at large use, the model which describes the properties of the system and the phase transition is a kind of a Richardson model, which also allows rather exact solution. So now I will not go in very much mathematical details, but let me describe the basic steps of treatment of this model. The first attempt would be the mean field treatment. This mean field treatment is a typical, it became a standard in the SYK model. And what we did is also the extension of this mean field treatment to the SYK Hamiltonian modified or extended by the Hubbard interaction. And basically one writes partition function for the model and the action, and one introduce some fields, and those fields in usual terms correspond to a normal Green's function G as a function of time difference. The only continuous variable in this system is the time. In that case, tau is the imaginary time. So G is analogous to the normal Green's function. As one can see, it is averaged over the whole sides of the model. To this G, there is another important quantity which enters the mean field saddle point equations. This is the self-energy part for the normal Green's function, which is sigma. And G and sigma, one can write the diagrammatical Dyson equation, and sigma is exactly that is meant as a self-energy part to the for the function J. But because we have this attractive Hubbard interaction and we expect superconductivity, to describe it, we introduce also anomalous parts of Green's functions, or Borkov parts, which are called F. If one can see, this is the average over whole size, but this is the anomalous correlator, anomalous average of two annihilations, annihilation operators, and F bar the same for two creation operators. And for those two anomalous parts of Green's functions, there are also corresponding anomalous self-energies, which are called large sigma, self-energy parts. Those entities, if one writes down saddle point equations, that basically the saddle point equations reproduce exactly the diagrammatical Dyson equation or Borkov equations for this Green's function and self-energy parts.
May I ask a question concerning the mean field approximation? So you consider this G as a random function, so it varies from side to side randomly. Is it correct? I mean,
it's correct, but yeah.
And the question is it correct? I mean, to use mean field approximation?
The mean field approximation is justified because n goes to infinity. So we consider the limit n to infinity. It is all-to-all coupling with, and the mean field is justified because n goes to infinity. And meanwhile,
so long range interaction, yes,
infinite range.
Infinite range.
Mm-hmm. And this is what justifies mean field treatment.
Mm-hmm.
Basically, after doing this mean field procedure, without going into details, one arrives at the set of mean field equations. For G, this is the normal part of the Green's functions. I forgot, and which is important, of course, that there is another field which will play an important role, delta. Delta is what one would associate with a local superconducting order parameter, which is basically, as one can see, it is time local and it is site local at each given site. It is basically important because why I stop on delta in details? Because if one looks at those two parts of the Hamiltonian, one can see that the SYK part represents basically infinite range interaction, all to all. Hubbard part, Hubbard U, is site local. It is not all to all, but it is, and this is in that sense they are very different in the sense of the localization properties action onto the model. U is only at each given size, and this is an important fact. And that is why one needs to to deal with U, one needs a local superconducting order parameter. Whereas to deal with the SYK part, all those parameters which participate in the mean field are, so to say, global in the sense that they are average values over all sites. So now if one makes mathematically develops mean field treatment, one arrives at the following mean field equations. The first four equations can be interpreted as a result of Dyson equation, as I told, for normal and anomalous Green's functions, and then for delta. Another equation is for delta, where one can also see that delta divided by U is as expected. One can see it also from the definition. This is nothing else. There's up to the sign. It is F anomalous Green's functions at coinciding times, which basically can be followed from the definition. Anyways, solving this equation, those equations allow solution, and which can be analytically analyzed. It is basically approximate solution, but in very good approximations, one can obtain the following. That one can, for the superconductivity, first of all, one looks at, on the superconducting order parameter delta. And the solutions which are shown here in the right part of this slide are solutions for zero temperature. At zero temperature, one sees the following, that first delta is exponentially small, but appears at any infinitesimally small u. So any u, however small it is, as a solution of mean field equations, it generates a value of delta, which grows exponentially with growing u, as it is shown here. It is as low, and there are two. Then the second part is that this superconductivity, the behavior of superconducting order parameter, is different in two different regimes. First regime is small u, small in comparison with, again, with the SYK variance of the SYK couplings J. And then delta is exponentially small, or large U. Large U is basically a regime where you can think about all this as a hopping of pre-localized Cooper pairs, which are hop over the system. And in that case, delta is just U divided by 2, is proportional to.
May I ask a question?
Yeah.
About this limit J much smaller than U. Let's assume that J is equal to 0. So what we have now, we have a negative, sort of negative U Hubbard model without one particle.
Exactly.
So what we have just pairs sitting on sides, disconnected. Exactly. Can I call it superconductivity?
No. You cannot, physically, obviously not, because you have no phase coherence. Mathematically, you will get this delta.
All right.
Yeah, you're right. It's very correct. It's very reasonable question. It is indeed so that, as I say, what is written here is what is given by mean field, and you're completely right. Yes, you can say, okay, I see U delta. There is a delta, but physically they are disconnected sites. It should be not superconductivity here.
May I comment on this? Does this mean that in a large U limit, you cannot believe in mean field approximation, because at least one of the interaction, which is very strong, is local? I mean, it's not long range. It's a on-site interaction. It means that it maybe doesn't describe properly.
In reality, what happens, I can, I will stop on this. I will tell about this in the second part, so to say, of my talk. But in the large U limit, just to give you the superficial, into my intuition about this, switch off J. If you switch off J, you have a flat band. Flat band of Cooper pairs, so to say, localized, which are flat band, no kinetic energy.
It's pairs, flat band of pairs.
But now, and there is, of course, with J exactly equal to 0, there is no superconductivity, definitely no coherence. But because of this is a flat band, any infinitesimally small J will make drastic changes to the ground state, as is typical for flatbed systems. And in that case, one can show that any infinitesimally small J will establish coherence between the phases of those pre-localized, so to say, Cooper pairs, and go to and render the system superconducting.
And
So
effect of this J can be calculated.
Yes, I will show those calculations.
Peculiar thing in large J limit, it's unstable with respect to J, small J, small U. Sorry, in large U limit, it's unstable with respect to small J. So that's one of the
yes, and but let me if it would be it's not that quite that simple. Namely, in large U limit, it will be so as you say, and in small U limit, which I will consider right now, the things will be different, a little bit different.
Okay.
Which I will be talking in the next. So now this is the mean field equations. Let
me just ask another nasty question. So in this precisely this limit, when U is much smaller than J, you say that you from your mean field calculation you get an exponentially small but non-zero gap. Is it possible that corrections beyond the mean field approximation will actually destroy this gap?
Yes.
Make it zero?
Yes. I will show about. I will talk about it. Let's just few minutes, and you will. I will go it in this question in much detail. So. And it is not distraction. So let me just tell you the story further. So this is the mean field. Now, complementary to the mean field, one can do exact diagonalization of a model with finite number of sides, and we can proceed up to the 12 sides. And let us look at the exact results. Numerical results of the exact diagonalization of this model with a finite number of sides. First of all, we can consider the many-body energy spectrum, and this is on this left panel. This is a many-body energy spectrum with a different number of sites and for the system with different number of fermions, and the system consists of maximally 8 sites. So 16 fermions at most, 2 fermions on each side can be put spinful. So what one can say? So each this number is a number of fermions. So this is the system. For example, this column represents the spectrum of system with eight fermions and 8 sites. So half filling, one can say in that sense.
Can you tell us the parameters, please? The other parameters, J and U and so on.
Everything is measured in number of J. So J is 1 as a universal energy scale, and U here is a 2 times J.
Thank you.
And this is the spectrum, and one can see there is a ground state and then excited states and so on. One can first of all, if one moves in the direction of changing the number of fermions, then first of all, one can see even odd alternation. I should say U is 2 times J. Thank you for this question. It means that we are in the regime of large U, relatively large U. And in that case, one can see, first of all, of course, even odd alternation, which should be expected. But second, if one now considers only the even number of fermions, which means this is the situation where the system rather would be superconducting without any contamination, so to say, then one can see that there is a gap between the grounds. There is a ground state, and there is also always a gap between the ground state and excited state. But now, if one concentrates on this, and what one also those states, which I call the states, they are basically not a single states. They are bands. so to say. Because of J, each of these ground state is not, there is not a single state here, but there is a band, this lowest line here denotes, marks basically the number of states, just a bunch of states, which is shown here, so to say, with larger resolution. This is only this is the lowest band. One can see the energy scale here is quite small, around 0. And one can see that in this band, there is also always the gap between the real ground state and the first excited state.
May I ask, is there anything like fill-in factor, ratio between number of electrons and number of sites?
Here,
where it is here?
Yes, of course. This is 16 sites. Always in all this graph is 16 sites. So 8 electrons on 16
sites. How many
sites.
electrons? I mean,
8 here for 16 sites, 10 electrons for 16 sites, 12 electrons.
I think you said 8 sites, not 16 sites.
Oh, sorry, I'm sorry, 8 sites. Sorry, yeah, 8 sites and 8 electrons, 8 sites, filling 1/2.
This is number of electrons. Okay.
Yeah, yes. Number of electrons 8, number of sites 8. Filling factor 1/2.
If filling factor is 1, do we have excitations in this case?
No, as you can see here, this 16 is sorry.
No excitation or what?
No excitations.
No excitation. Okay.
Everything is filled.
So it's unpaired. Excitation is unpaired electrons, so to speak, in empty sites.
Yes, exactly. Yes. Wait, I have to. Something. Yeah, great. You can see then full screen. Full screen. Okay. So, anyways, what I wanted to talk about it. So, if one concentrates of this lowest band. What is this lowest band? It means that this lowest band determines the ground states where no electron is excited, so to say. So all basically there is a pairs that consists of the band which describes the motion of pairs through the system. And in this band, there is a gap between the lowest state and the first excited state. If one looks now if one varies and analyzes this makes a calculation in which one now varies U with respect to J and analyze and concentrates on the behavior of this gap between the ground state and the first excited state in the very lowest band. All this is already, so excited states are thrown away. Then one can see the following picture, that this gap starts, it is numerically, one can say 0. And then it starts to grow linearly with U, but not at 0 U, but there is a finite threshold U. Here. This is the result of numerical calculations, exact diagonalization. Now, this is about the many-body spectrum. Now, this, and again, this result suggests that maybe at 0 U, it's very small U, you do not have superconductivity in the sense of the energy gap. There is no gap here. The gap starts only at finite U. There is a finite U threshold, which is a contradiction to the mean field behavior. Of course, mean field is for infinite number of particles and numerical simulations are for very finite number of particles, but nevertheless, there is a contradiction. Now the next question is how to analyze the gap is very so rough property, and maybe this is an artifact of finiteness of the number of particles. So how to analyze numerically, or how to to get from this numerical data the answer to the question whether there is a superconductivity in this, whether the system of finite number of particles with finite number of sites is superconducting. Because usually superconductivity formulated for infinite range for systems with infinite volume and infinite number of particles. Now, Method to analyze it is the following. It is very well, actually very well known for the physics of cold atomic gases, where you typically have Bose condensation, so finite number of particle atoms in the trap, and you face exactly the same problem. You should determine whether there is a condensed phase of system with finite number of particles. The answer on this question is the following. Let us analyze. And why this analysis is necessary? Because obviously, if one looks at the delta which was introduced in the mean field, then numerically, well, it is nonsense to calculate this parameter with a system for the system with finite number of particles. It will always be 0 in any state. It is non-diagonal, and that's why what one does is the following. One analyzes the density matrix of the, so to say, Cooper pairs, if I can say like this, in the following sense. One introduces the operator B, which is a creation of a Cooper pair, electron spin up, electron spin down, B dagger, and correspondingly operator B. Then one can calculate exactly the so-called reduced density matrix, which is the average value of creation operator B dagger at the site E, B at some other site J. This operator is diagonal in the total number of particles, and that is why this average is non-zero. And this average creates a what is called reduced density matrix.
Is it fermionic operator B or bosonic?
Bosonic. B is bosonic operator. So, and now there are two possibilities, namely, if there is, so now one can first of all look at this reduced density matrix, and then there is some matrix, which is basically at each given realization there are some random numbers, but nevertheless one can diagonalize this matrix and analyze the spectrum of eigenvalues of this matrix, and one can of course arrange those eigenvalues in the from the largest one to smaller ones. And then if there is a condensate wave function, if there is a condensed state in this system, then the eigenvalue of the reduced density matrix, which corresponds to this state with macroscopical occupation, which corresponds to the condensate, should be much larger, exactly to say of the order of the number of particles. It should be proportional to the total number of particles and grow with it. And all other states which do not correspond to the condensed state should have some eigenvalues which are of the order of 1. So the signature of off-diagonal long-range order in the finite size system is the presence of a single eigenstate which grows with the number of particles linearly, whereas all other eigenstates of such reduced density matrix are some numbers of the order of 1 which do not change substantially with the number of particles. Now, on the right-hand panel, there is an analysis of the spectrum of the SYK model exactly for this situation. This is analysis. Again, U is equal to 2, so large, regime of large U. And this is the analysis with different number of particles in this system. Again, and in that case, following, the system is always taken at the half filling. So the number of n of sites is exactly equals the number of fermions. 8 fermions, 8 sites, 10 fermions, 10 sites, 12 fermions, 12 sites. On the vertical axis, those are the eigenvalues of the reduced density matrix, and one can see that there is a, and one can see that there is a single one, which is the largest one, which indeed grows almost linearly with increasing n. And this is the signature that there are a bunch of eigenstates that basically do not change substantially with increasing n. And there is a single one which grows linearly with n. And this is exactly the signature that indeed at large U numerically one can prove and see that there is a of diagonal long-range order and superconductivity in the system at 0 temperature at large U. Now, one can furthermore analyze, so therefore, instead of looking at delta for numerical simulations, what one should look at is in order to qualify whether there is a superconductivity for numerical simulation is this largest, or the difference, the gap, the difference between the largest value of lambda of largest eigenvalue of the reduced density matrix and the next largest, lambda 0 minus lambda 1. And this gap should exist and grow with the number of particles. If this gap is large, of the order of the number of particles, then there is a superconductivity.
So you're talking about gapless superconductivity in some way?
It's not a gap in the spectrum now, in the energy spectrum.
No, you say gap might be 0, but you still have superconductivity with a 0 gap, but with a large eigenvalue lambda.
I say, I don't know about, I did not say about the gap in the energy spectrum. I did not refer to this basically.
You show the graph that up to certain Hubbard value, you have 0 gap.
To avoid my misunderstanding, this graph is for U equal 2. And this one, where there is no gap, is U equals 0.2.
How lambda became
different regimes? Quite different regimes. The graph I showed you for lambda is somewhere here already, where it is definitely superconducting according to the energy considerations. So now, well, so basically, again, so this difference, now I will say is this is something.
Sorry, I have another question. Yeah, can you please go one page back? Yeah, no. Forward? Yeah, this one again. So you change here the number of what? Of particles.
Yes.
But you
and
fix
sides together. I change the number of particles and sides such as to keep the filling factor.
Here you change the number of particles and number of sides.
Yes.
Okay.
Keeping them.
Which you didn't do before in some other plots which you showed.
No, I didn't do before because before I just looked at the energy kind of gap, and now I want precise understanding how to how to see the superconductivity in these finite size systems. And I understand the following, that in order to see the superconductivity, I should look at the spectrum of eigenvalues of reduced density matrix, and I should look whether there is some single eigenvalue, which is the largest one, with which is much larger than all other ones.
Thank you.
And now I know. Now the next few two graphs, which are already more precise analysis of presence of superconductivity, are the following graphs. Now I investigate the difference between the largest and the next largest values of the reduced density matrix as a function of U, which now in the numerical calculations as a result of in the results of exact diagonalization. And then I can see again the following picture. Then Fu is small till 0.25 approximately, as one can see here. There is no gap. There is no difference, gap in the sense difference between the eigenvalues. There is no difference between the lambda 0 and lambda 1. It is almost 0, which means that my system of finite number of particles does not show any features of condensation. The matrix, the reduced density matrix, corresponds to a normal system where each eigenvalue is approximately the same. Starting from 0.25 approximately, and if U is higher than this, higher than 1/4, then one can see that the gap starts to develop. And one can see that there is a lambda 0 starts to rise, and one can now, according to the previous considerations, associate this rising with the appearance establishment of superconducting order in the system. And again, an important feature of this, which is in contradiction with the mean field, is that there is a finite U necessary that the superconductivity appears. The mean field told us, no, any U will work. The numerical, and of course, mean field is large N, but mean field ignores a lot of fluctuations and so on. And in that sense, numerics is kind of experiment. And moreover, the same tells us the energy analysis. If one just calculates the energy gap in the many-body spectrum, again, reproducing the results I already showed, but on the larger scale, then again, there is a gap starting to appear only at finite U, which coincides with the U which was obtained from the analysis of the eigenvalues of reduced density matrix. So numerical data show consistently that following fact, that there is a finite U necessary to create superconductivity. Analytical data resolution of mean field tells us any U will work. So what is, something is wrong, and probably with mean field. What is wrong with the mean field? And this is the question I will I will answer here. Basically the following, and then we come, and in that sense, we go to the problem of the answer of the question, what is wrong to the mean field, leads us to the new physical picture, which leads us to the analogy between the superconductivity in SYK model and the well-known Kuramoto model of phase synchronization of harmonic oscillators. But in that case, in the case we are considering, there is a, so to say, quantum version of Kuramoto model, which I will introduce right now. So basically first, what is wrong with mean field? They say the following fact. Mean field assumption is that delta is the same on all sides. That was just an assumption. But in reality, delta is some complex number. And it is reasonably to assume that the amplitude, the absolute value of delta is the same on all sides, but the phase can be very different. The phase is a local parameter, and one should actually consider delta as a amplitude and the phase. Mean field, if one goes into details of mean field equations we were considering, I will not go in mathematical details, but one can show that actually they are written exactly for absolute value of delta, which is indeed non-zero. But in those mean field equations, the phase has been lost underways in mathematical treatment. So why it happened? Because this is the effective action, basically, which follows from the mean field treatment. This is how it looks like before one. This is the effective action, and in this effective action, indeed here there is a delta absolute value squared, so the phase disappeared. But in this logarithm, which comes from the fermionic determinant, for those who knows about the integration of fermions and so on, there is a fermionic determinant, and here delta comes local at each side. Here is a sum over all sides, and delta comes local and with the phase. So one should write this one as absolute value and e to the power I phi I. Again, interesting structure of this logarithm is the following, that it combines local delta, site local, I mean, which has an index I, and global, site global properties of normal part of the Green's function taken from the SYK model. One can say the following. The first, mu is the chemical potential, it's kind of less trivial, but sigma, this is a self-energy part of the Green's function for the SYK model. Because of all-to-all interactions in the SYK model, infinite range, this sigma does not have a site index. It is global, acting on all sides equivalently. At the same time, superconducting order parameter delta, I will call it superconducting order parameter in quotes, delta is local and has this delta has this phase e to the power I phi as a phase of the superconducting order parameter. Now, let us think about what happens if sigma starts to fluctuate. This sigma. Let us consider mean field. Mean field fixes all those values through the mean field equations. But now, what happens if now sigma fluctuates around the mean field? What happens is the following. If one expands those logarithms, then one can imagine sigma as a background, fluctuating background, which connects all the phases of all those delta i's. Why? Because sigma does not depend on I. This is like you have a number of oscillators coupled together with this coupling sigma. This is maybe now a little bit hand waving, but if one does it mathematically exact, then the picture I showed you can be also, so to say, made mathematically exactly with the help of diagrammatic expansion around the mean field action. And what is the aim of this diagrammatic expansion? The most important part of all those diagrams, which I showed here, is the following. How is it possible to provide correlations between the phases at different sites from this action? Why this question is non-trivial? It is because, as such, this action represents the sum over each site. And basically, if one considers this sum, each term is local, site local. How from this site local terms how one can produce out of those number of site local terms, site non-local interaction between the phases? The answer is the following, that basically this interaction diagrammatically is given by this diagram, which I will explain a little bit in the lowest order. So what happens is the following. Assume, so this is a diagram which characterizes the establishment of connection between the sites, between the phases of superconducting order parameter at different sites. Assume that there are sites I and j. In each of those sites, the elementary process looks like the following. There are two fermions that can be emitted from the sites I. And those two fermions, there are another two fermions that they are also emitted from the other side, from the site, other side K. There are two Cooper pairs at the beginning, site I, site K. This site K plays an auxiliary role. And the relation happens between due to the correlated act of scattering of SYK model. So one can two sites with two Cooper pairs. All those sites emit at all 4 electrons. 2 electrons with spin up and spin down here collide with each other, interact with each other, and are transferred, one to the site L, one to the site J. Another 2 electrons also collide and are transferred again to the both sites L and J. So basically, what this diagram describes is the hopping of at all 2 Cooper pairs, again the same as we told as was seen in the regime of large U. You have two Cooper. So in this case, there are 2 Cooper pairs, 2 correlated scattering events, and those two which are described as those two vertices, and as a result, 2 Cooper pairs are transferred from sites I and K to the sites J and L. Now, transfer from K to L plays here the role of, so to say, agent. This is auxiliary. It is not very interesting. Interesting is that, which we will follow the transfer, the correlation which is established from between the sites I and J through this correlated kind of hopping. If one calculates this diagram, the most important thing is the following, that one has the term which establishes the relation between the phases phi I and phi J. And which means basically this, that because one has a possibility to transfer Cooper pairs over all system due to the SYK coupling, this SYK coupling is able to establish phase coherence between the Cooper pairs at different sites.
This is Josephson effect, I mean, between sites. So to speak. If you
Josephson with only with the following almost, but Josephson usually one thinks about the usual single particle tunneling. And here
you also have this second order. I mean, you have this transferring pairs due to G. I mean, and if each pair carry phase, this transfer of pairs due to G in second order depends on difference of phases. Because
in that sense, you're completely right. This is kind of
your superconductivity is Josephson array of sites. Yes. Each of them build its own phase, but phases are coupled due to Josephson effect.
Yes, you can. This is correct understanding. And then, so after one, now there are some peculiarities that this diagram is not enough. One should sum up the whole series of those diagrams. But anyways, after one executes this program, what happens basically is that one arrives at the following action for the phase fluctuations alone. So this action one should consider as the following. Now the total action is the sum of the saddle point, which I did not written here, the section that is solved by saddle point solutions, and separate action, which describes the phase fluctuations or coupling of phase fluctuations or array of Josephson junctions, whatever you call it, which is written like here, which is written here in red. And this action actually is nothing else as a quantum version of the so-called Kuramoto model. The Kuramoto model describes coupled classical oscillators in presence of noise, usually external noise. So here, due to this term, there are coupled quantum. This is an action, and this action represents coupled quantum oscillators, Josephson junctions, and m½ is kind of a quantum noise. Now, this action can be analyzed and basically can have two phases, and the analysis of this action basically what one can expect. There are two phases. First phase, if the kinetic term, I will call it phi dot, if this term dominates and the coupling J is small enough, then basically all phases are uncorrelated, and each phase fluctuates randomly from between 0 and 2 pi. However, if J dominates, then due to this cosine term, the phases try to align so that the difference is 0. And all phases are aligned, and this marks the real phase coherence and the off-diagonal long-range order, the same superconductivity in the system. Now, the analysis can be done, the analysis of the ground state can be done with help of the relatively simple quantum mechanical considerations, namely the following. One, it is reasonable to assume that the ground state of these Hamiltonian four phases is symmetric. And in that sense, we consider this as a Bose condensate with kind of wave function psi, which depends on phi as a variable, and formulate the Gross-Pitaevsky then one can formulate, write down the Hamiltonian, nonlinear Hamiltonian for the corresponding action, and formulate write down the Gross-Pitaevsky equation for the wave function psi as a function of the angle phi. And this is this equation explicitly, which is written here. And then one can introduce the, so to say, order parameter. What is our order parameter? Is the value which is shown here as ρ1. What is this? ρ1 measures the average of the cosine of the phase in the ground state. If the ground state is unsynchronized, or uncorrelated, normal, then of course phi is smeared and average value of cosine is 0. The superconducting of phase synchronized state will correspond to non-zero value of this ρ1. And that is why ρ1 can be taken as an order parameter of the synchronization transition. It is 0 in the unsynchronized phase and it is non-zero in the synchronized phase. Now, in that way, one arrives in the following two equations. The first one out of the Gross-Pitaevsky equation becomes a so-called Mathieu equation, which looks like this. It has, and this equation, which stays here, is nothing else as is called in mathematics Mathieu equation, with effective constant coupling constant J ρ1. The non-trivial, the non-linearity is from the Gross-Pitaevsky equation, is in the fact that ρ1 itself should be determined self-consistently out of the wave function obtained from out of the solutions of the Mathieu equation. And this is now this analysis can be done completely. And basically the phase transition can be determined, for example, in the following way. One assumes the wave function as kind of a condensate and some fluctuations around the, as a condensate is assumed as a uniform solution ground state. And this is an unsynchronized phase. If the wave function is just this independent of the angular variable phi, then it means that all phases are smeared from 0 to 2 pi, and this is there is no synchronization, no phase coherence. But then we can introduce the fluctuations around these solutions and look at the following, substitute it in the solution of the equation and look on the spectrum of those fluctuations phi L. One can easily diagonalize this spectrum and find that L phi with the number plus and minus 1, correspond psi plus and minus 1, which corresponds to the function I phi and e to the power minus I phi, has the following frequency dependence, which is shown here. And one can see 1/2m is the measure of the, so to say, kinetic energy, if one wish, or quantum fluctuations of phases. And one can see that this root has 0, becomes 0 if G is equal to 1/2m. And at that point, the corresponding mode is a soft mode. The gap vanishes and it signals the phase transition, the synchronization transition in that case. What is important that this synchronization transition happens not at any G, but at a finite G. The graph of this is this finite G, this is a graph, this is a behavior of this mode, red line, the frequency as a function of mg. And one can see that this is, and from on the other side, here the blue dots are the solutions for the ρ1. And one can see this is a analytical, in that case, analysis of this equation. And one can see that at the point G equals to 0.5, 0.5 in the sense m equal to 1 in that case, one can see the transition. One can see that the mode becomes soft, and at the same point, the order parameter, synchronization order parameter ρ1 becomes finite. Now, yeah?
I just want to mention one thing. In usual superconductivity, if you have granular array of superconducting dot, there are two transitions. One transition is when dot becomes superconducting, but there is no global synchronization of the phases between different dots. And then second transition when global superconductivity appear. Here is the same thing if you take this concept of Josephson coupling between sites, which are paired, first paired, and then synchronized. Pairs become synchronized. You have this delta first, and then global superconductivity appear later.
I agree. I agree. This is absolutely the same picture. Thank you. Yeah,
Okay.
this is the same picture. Now, what is important in now? Why does it? So important is here in with respect to the initial model and with respect to the resolution of discrepancy between the mean field data and numerical data. Important is that there is a finite threshold J, and this G constant it relates to the U, which is, I will go back. So here, now, the important formula is that if one looks at G, this is the constant G, which enters the Kuramoto model. I will call it Kuramoto model. Important is, it depends on U. Finite G, finite value of G requires a finite value of U. And this resolves, so to resolve the contradiction between numerical and naive, I would say now, mean field solution of the problem. So in reality, the naive mean field solution, again, as you say, it looks like establishing of local superconductivity in each dot, if you wish, if you consider it as a Josephson array, but it is not enough to establish, in order to establish the global off-diagonal long-range order, the phase coherence. And only finite U is necessary to establish the phase coherence. And altogether, it means that the phase transition, this critical point, is described by the so-called Kuramoto model, the phase synchronization. So the real transition which appears to the superconductivity increasing U in this SYK+U model is the phase, it has a character of phase synchronization transition, which is, and is described by the effective model, low energy model, is the model for fluctuation of phases. Now, now let me do short summary of this first part of my talk. So then, first of all, so one can see that the local pairs appear at any negative U, but those pairs are not correlated. What does it mean? That means, it means first that if one considers now with respect to the measurable properties of SYK model, the single particle Green's function does not feel any fluctuations of those phases, and this single particle Green's functions feels already the appearance of this delta in the sense that in time it starts to decay exponentially in time at large times with a time scale that determined with this energy delta, which is the absolute value of delta. Despite those delta are non-synchronized, which means that the delta in this small u regime here, the deltas are non-synchronized and you do not have superconductivity. But at the same time, the single particle correlation function of electrons has not power law decay for long times, but exponential decay with the energy scale, which is determined already by this energy gap. What does it mean? It means basically one should expect, but that at very low temperatures, this system is not conducting, but rather insulating. This is what I told. I can expect that at low temperatures, with any finite U, at very low temperatures, the system will be not SYK conductor, but insulator. One can call it SYK insulator or simply insulator, but anyways, the conductivity will have small, tiny thermally activated behavior with very small gap. This gap might be exponentially small in U, but nevertheless, it is finite. And at higher temperatures, of course, one can, the power law decay of correlation functions of usual normal electron correlation functions prevails. And one should see usual, so to say, unusual, but incoherent metal, the strange metal behavior, which is predicted by previous studies of SYK because the temperature will be much larger than this tiny gap delta, and then this gap can be disregarded. So therefore, in this regime, there is a crossover between the insulator at 0 temperature and incoherent metal at finite temperature. And off-diagonal long-range order, the true superconductivity develops at some critical U. And this transition, as a quantum phase transition, is characterized by phase synchronization between the phases of already existing Cooper pairs at different sites. So this is the first part. I think there was a lot of questions. So if you, I will, and I see that there is a lot of time passed, but because there were questions, probably I will, if you don't have questions to this part, I will proceed with the second one, which is basically analysis of the model. We already talked about this analysis in the regime of large U. So now in the superconducting phase, U is large, and already the picture is in large U is the Richardson model, so-called Richardson model. Let me introduce the physical picture. We already discussed it, and very shortly, one understands that there are very well preformed, so to say, pairs localized at each site. U is very large, and J is now only a perturbation. And the picture is the following. Yeah?
Yeah, sorry. I mean, I think it's already an hour and a half, so I think you can, if you could briefly describe the results of the second part.
I'll do it rather briefly. So there are pairs, and basically the picture is the hopping of the Cooper pairs as assisted by these SYK hopping terms. And the Hamiltonian can be written where if one considers the hopping, then basically one can understand that only two pairs can hop simultaneously and coherently from one side to the other. And basically the Hamiltonian in terms of those bosons can be written as is shown here. What is important here? It looks like bosonic SYK model. B are bosonic operators, hop over the lattice, but the hopping matrix element is J squared. What does it mean? It means that there is no Gaussian distribution of J's, but J's have finite value in which is positive, because all J squares are random but positive numbers, positive definite. So there is no non-random positive part, and assuming that this non-random part, positive part is the major part, one can then transform this model to the following, that just throw away the random part, which we did to analyze this situation. If one basically substitutes J squared by average value of J squared, which is called here divided by 2U W, this is the W, then one has the following model. Now we have a non-random model of hopping of bosons. Four particles, if we want. So two bosons are annihilated, two other bosons created over 4 sides in the whole model. Now, importantly, because it is all-to-all hopping, one can introduce new, so to say, super bosonic, if you wish, operators B0 large, which is just the sum of all B operators over all sides, and then rewrite this Hamiltonian exactly in the following sense. So here there is an operator of single boson B0, but there is also fluctuations which are described with NB. What is NB? Is the number of initial bosons in the lattice. Bosons, not fermions, but bosons, the number of Cooper pairs. So filling factor differs correspondingly. Further important step is the following, that if one analyzes commutation relations between B0 and NB, then one can see that those commutation relations exactly reproduce a spin SU2 algebra. So one can rewrite this model. I will rather brief because of time, but one can rewrite this model on a spin language where B0 is L minus, B0 dagger is L plus, and Z component of spin LZ is combination of number of bosons minus half of the number of sides, basically the filling factor. And in that case, one can, if one rewrites it as a model of a single spin, one can diagonalize this model exactly and determine the full spectrum and exact spectrum. For example, here is given by a half filling. Number of bosons is exactly half of the number of sides. one has the energy, and the energy, total energy spectrum or energy values are numbered now by the total angular momentum of the system. And with a given only to the given angular momentum, there are now a number of degenerate state, which is here. This is the degeneracy level, and the ground state is given by L equals to n½ angular momentum. This all in terms of spin, which can be, but the spectrum can be then analyzed exactly. There is an energy gap between the first excited state and the ground state. This energy gap is now due to the hopping of Cooper pairs. And this energy gap is half of this W of the strength of the hopping. And now again, so this data for single particle density matrix, I will not reproduce. This is already shown here, but basically what is important that, and in terms of on the language of the spin model, one can now, of course, determine the density matrix exactly. And determining this density matrix, one can drive this line with for the highest energy, for the highest eigenvalue, and one can see it reproduces at the larger n, the closer is this line to the exact, to the numerical simulations. And finally, one can go, if one knows the spectrum of the model, one can analyze what happens at finite temperature at the point of the phase transition. And then one can calculate the free energy of the model. And skipping the details of the calculation, basically one can, if one knows the spectrum, one can calculate partition function, and one can calculate then free energy density. And then the ground state is determined, of course, by the minimum of the free energy density. And then here, what happens here is those three lines are free energy density calculated as a function of L. L is the total angular momentum divided by angular momentum per site, total angular momentum divided by the number of sites for three different temperatures. What one can see is the following, that at low temperatures, total angular momentum, the free energy has a minimum at 0.5. This corresponds to the superconducting phase. And then at higher temperatures, one can see that there is a critical temperature where another minimum appears first, and then the second minimum at this point crosses the lines, or minimum, the two minima switch, the minimum for the superconducting state and the minimum for the other state, which is a normal state, basically. Importantly, there are two minima and with a finite gap in L between those two, which means that the transition at finite temperature is of the first order, which is predicted here, which is another peculiarity of this model. So for this Richardson model of hopping of boson pairs, finite temperature phase transition from the superconducting to the normal state is predicted to be the phase transition of the first order. And this also illustration of the numerical data, which also illustrates this phase transition. It is not, from this data, one cannot conclude whether the order of transition. It only illustrates that the transition really takes place. This is again this largest eigenvalue and the gap between this largest eigenvalue and the other ones. This gap disappears. And then let me go then to the conclusions of my talk. So we introduced as I can say, probably the minimal extension of the SYK model, which leads to the superconductivity, the simplest one. And basically the simplest extension results in the superconducting phase with a number of peculiarity with regard to the phase diagram and kind of phase transitions between the normal and superconducting phase. And all this phase diagram is now characterized, we can characterize it in the following sense. So one has, first of all, at zero temperature, there is a phase transition for a finite value of Hubbard attraction, finite threshold value. In this phase transition signals the synchronization, phase synchronization between the phases of superconducting order parameter, which is already present at different sites. which means also that before this transition at small u, at 0 temperature, the system becomes insulating from the conducting as SYK. And rising the temperature in the regime of small u, where the system is non-superconducting at the beginning, one has a crossover from insulating behavior to the incoherent metal described by the SYK model. Then within the superconducting phase, at large u's, one has the regime where the model described is described as the Richardson model, which describes the hopping of the Cooper pairs over the lattice. And important for this Richardson model, it allows exact treatment, and one can see that the phase transition is predicted between the superconducting and normal state at finite temperature is of the first order, described by this such a so-called generalized Richardson model. That's basically all for my talk. Thank you very much for your attention, and I'm open for further questions and discussions. Thank you.
So thank you, Alexander, for this talk. Let's see if there are some more questions from the audience. I think we had quite a lot during the talk itself. So
yeah, it's already almost 2 hours.
Yeah, and I think there are only few people here still in the audience, but so the hardcore,
yes,
of it, I guess. Just one short question. So when you introduce this term, this Hamiltonian part U, to me it looked pretty much like the YSK part with just saying abandoning the randomness assumption about the J's. So some of the J's. So you basically put in some kind of order in your your J's. Is that wrong or not? What's
I don't think no, I think it's rather in the
well, I'm just
I don't think it concerns J from the following reason. First of all, the number of U's, so to say, the number of terms where I introduce this local order is of the order of n.
Yeah, I understand that, but I mean, basically, you just have J's which couple, you know, all different 4 sides in general with each other. But then some of these J's get some additional number which you call U, and these are those J's where all the indices are exactly the same. So I'm not debating. Yeah. So that means you kind of put in some kind of order in your set of J's.
Yes, kind of yes, but this order is of the, how it is called, of the measure 0 concerning the total number.
Well, it apparently has quite an impact, right? Because
but it does.
Right. So right. But then the question is, so you chose Hubbard because many people know Hubbard, you know. So this, what can you say in general? What kind of order do you have to introduce into your random J's in order to get similar interesting things? Maybe you don't have to add precisely these Hubbard terms, but maybe there's other, and so on and so forth.
Sure. Yeah, I mean, but I can, what is, that's not me, but other people did the following. They introduced, well, very specific symmetries in J's, so which means that they modify distribution of J's in such a way that this JIJKL, if you exchange the indexes K and J, then this term should change sign, but only K and J and not I and L. And don't ask, sorry, I cannot answer the question because it's not my work. I can't answer the question why so. I also cannot argue why it is natural way. But this leads to the kind of superconducting order. Why I say kind of? Because it may, you see superconducting instability, which means that you see that there is a minimum in the superconducting solution. But if you compare that, but the second thing is whether this minimum of, so to say, free energy is the real minimum with respect to the others. But nevertheless, this is one way to introduce superconductivity. Another way is to introduce additional terms into Hamiltonian SYK, which are not of SYK kind, which are the following. So, suppose you have SYK, and you couple them to some of number of phonon modes with random frequencies, which is basically again introducing indirect attraction, which is now random and non-local. This is another way to modify the Hamiltonian, which leads to the superconductivity. This way is described by the work of Esterlis and Smalian.
Yeah, oh, okay, thank you. But coming back actually to your, so what is the physical motivation for you introducing this U? Because it looks a bit like, if you talk about small grains with all states coupled to all states in some sense, and then you suddenly introduce a U term, which looks a bit like coming from some screen-Coulomb interaction physics. So you assume that you actually do have quite some how to say, some understanding of a distance between different states. So some states are close, some are far in some space. So you have some.
So honestly speaking, the only reason for introducing U in such way is that I thought that this is the simplest possible way. Nothing more. So I thought that this is mathematically looks simple.
So let me take this to an extreme. Take this to an extreme and ask the following then. What happens if I take, so we agree that the SYK plus Hubbard is basically a modification of SYK, so that you add some, if you wish, some on-site corrections to your coupling constants J. But what if I now introduce some kind of fully symmetric SYK problem, where the J's, where I don't have any randomness anymore, but still some kind of non-trivial coupling? I mean, is there anything I can expect which would be also maybe leading to superconductivity in your?
If you make all J's in the sense, if you choose the sign of those non-random J's in such a way that you can interpret it as attraction between the Cooper pairs, or coupling which favors attraction of Cooper pairs, then you definitely will get superconductivity, or definitely, I think you will get superconductivity. I didn't calculate it, but I think I'm pretty sure you will get superconductivity. But
the interaction, I mean, to get superconductivity, not
your J will become interaction. Basically, your J will become interaction between electrons. If you now say those Ji, Jkl are non-random, is non-random, then and interaction all to all. And if you now introduce spins, look attentively to the spins and interpret it as can interpret this interaction as interaction between Cooper pair singlet pairs, which is attractive, then yes, great, you will get superconductivity. And this is okay with superconductivity. The thing is this, that one tries. Why one tried to keep SYK? Because at high temperatures, beyond superconductivity, one wanted to have incoherent metal. And this is why you keep this relatively complicated J's, which are random and so on, because you know those J's at high temperatures will give you incoherent metal behavior. If you might make those J's non-random, you will lose incoherent metal at high temperatures, which is
what will you get? What will you get then instead?
I think rather, that's a good question.
Non-linear temperature dependence of resistance.
Yes,
if it is coherent metal, like ordinary.
You see that those J are quite peculiar because there is no, if you would introduce single particle hopping, then you definitely will get Fermi.
But we don't have that.
Without this, I don't know. Quite honestly, I don't know. No answer, but well, I never tried. And I know this so that anybody tried. Good question, actually.
Isn't it if you have coherent motion of electron from one side to another, you have sort of band structure and then you don't get linear temperature dependence of resistance in this case. Only if you break this coherence motion and make it random, you will get linear temperature dependence. Is it correct that this change of temperature dependence is breaking of coherence of electronic motion?
This is correct. The second is correct. The thing is only this, that if J is non-random, I don't know how to answer. I honestly don't know how to answer the question if J is fixed. And then you have the system which has only interactions, no single particle hopping, and those interactions are fixed.
You have more complicated, but still quasi-particles moving from side to side coherently. So you have this dispersion law, and it's not very much different from
yeah, maybe it's hopping of kind of what they look like bosons or something like this. Yeah.
But of course, I also don't know. It's a guess. It's a guess. Oh, very interesting question. Do you need break to coherence to get linear temperature dependence in high temperature limit? That's an interesting question.
Yeah.
Or you get it only from this concept of pairing, that only pairs are coming from one side through the crystal, not single electrons. I don't know.
If the pairs are incorrect, but again, yeah.
It's open question.
It's open question. I don't know.
But it's always interesting, yes, of course.
Well, yeah. No, this question that I should keep open. I don't know the answer.
Okay, more comments, questions?
Okay, I have a question, if you hear me.
Yeah, I can hear you.
Yes.
Okay. And did you calculate some transition in the limit U smaller than G for temperature transition from incoherent superconductor to this strange metal? Incoherent superconductor, you call this insulator?
No.
Okay, because as I understand correctly, in this limit, there is some crossover or transition for high temperature phase.
Yes, well, what I think that altogether I did not first direct answer, I did not calculate it. Second, I think that it is kind of system which is thermally activated with a small gap. It is insulator with thermally activated transport, which has a small gap, but over the gap, over the gap, the transport is incoherent. So it's kind of, I don't know how to say it, how to call it. It's the question of the terminology. But what happens is the following: that lower than the gap, you feel that there is thermal activation. For the temperature higher than the gap, you have an incoherent metal, as SYK predicts.
Okay.
Exact crossover is not calculated. It can be calculated definitely, but I didn't do it.
Okay.
Yeah. So the phase transition is not there. It's the same. It's all the same phase. It's just the signature of transports, let's say. Here. And it should be resistance, should be linear, I guess, in T for up to some small temperature, but then it will rise. Resistance will rise if temperature will be below delta.
But point is, and even it's incoherent superconductor, then you have gap. Then if temperature is larger than gap, there are some quasi-particle transport and something like that. And question about what happens here, because it's okay.
Yeah.
Okay. Okay.
Okay. Seems like that's about it from the questions. So let us all thank our speaker.
Thank you very much.
There we go.
Thank you. Thank you.
Okay.
And yeah, and I think we already had an inbuilt sort of discussion session during this talk itself. So we don't need an extra discussion session, perhaps.
I
So
guess
think,
it's a bit late already. This is also because we started at 5 p.m. and then you probably have seen that a lot of people left because you all know that we have a cafeteria. It is still working in our building, but it operates at very strict times. So I think everyone ran away, especially those who need to get some food. And the ones who you see here are the ones who usually do not go to a cafeteria.
So it's not because of me, it's because of her cafeteria.
Yeah, it's no, it's not because of you. I don't think so. Right. But I think it's maybe a good idea if we do not add some additional post-seminar discussion, because I think now I also need some food.
All right.
Yeah.
Okay.
It was
very nice. Very nice.
So,
okay, bye.
Thank you all. And I'll end the session.
Bye to everyone. Bye, Robert. Bye, Mikhail. Nice to see you and hear you all.
Yeah, nice to see you. Thank you. Bye-bye.
Bye.